Neural networks are one of the most powerful learning algorithms that we have today. In this and in the next few videos, I'd like to start talking about a learning algorithm for fitting the parameters of a neural network given a training set. As with the discussion of most of our learning algorithms, we're going to begin by talking about a cost function for fitting the parameters of the network. I'm going to focus on the application of neural networks to classification problems. So suppose we have a network like that shown on the left, and suppose we have a training set like this of xi, yi pairs of m training examples. I'm going to use uppercase L to denote the total number of layers in this network. So for the network shown on the left, we would have capital L equals 4. And I'm going to use S subscript L to denote the number of units, that is the number of neurons, not counting the bias unit in layer L of the network. So for example, we would have S1, which is the input layer, has 3 units, S2 in my example has 5 units, and the output layer S4, which is also equal to SL because capital L is equal to 4, the output layer in my example on the left has 4 units. We're going to consider two types of classification problems. The first is binary classification, where the labels y are either 0 or 1. In this case, we would have one output unit. So this neural network on top has 4 output units, but if we had binary classification, we would have only one output unit that computes h of x. And the output of the neural network would be h of x is going to be a row number. And in this case, the number of output units SL, where L is again the index of the final layer, because that's the number of layers we have in the network. But so the number of units we have in the output layer is going to be equal to 1. In this case, to simplify notation later, I'm also going to set k equals 1. So you can think of k as also denoting the number of units in the output layer. The second type of classification problem we'll consider will be multi-class classification problem, where we may have k distinct classes. So our early example had this representation for y if we had 4 classes, and in this case we would have capital K output units, and our hypothesis will output vectors that are k-dimensional, and the number of output units will be equal to k. And usually we would have k greater than or equal to 3 in this case, because if we had 2 classes, then we don't need to use the 1 versus all method. We need to use the 1 versus all method only if we have k greater than or equal to 3 classes. So if we had only 2 classes, we would need to use only 1 output unit. Now let's define the cost function for our neural network. The cost function we use for the neural network is going to be a generalization of the one that we use for logistic regression. For logistic regression, we used to minimize the cost function j of theta that was minus 1 over m of this cost function, and then plus this extra regularization term here, where this was a sum from j equals 1 through n, because we did not regularize the bias term theta 0. For a neural network, our cost function is going to be a generalization of this, where instead of having basically just one logistic regression output unit, we may instead have k of them. So here's our cost function. Our neural network now outputs vectors in Rk, where k might be equal to 1 if we have a binary classification problem. I'm going to use this notation h of x subscript I to denote the ith output. That is, h of x is a k-dimensional vector, and so this subscript I just selects out the ith element of the vector that is output by my neural network. My cost function j of theta is now going to be the following, is minus 1 over m of a sum of a similar term to what we had for logistic regression, except that we have this sum from k equals 1 through k. This summation is basically a sum over my k output unit. So if I have 4 output units, that is, if the final layer of my neural network has 4 output units, then this is a sum from k equals 1 through 4 of basically the logistic regression algorithm's cost function, but summing that cost function over each of my 4 output units in turn. And so you notice in particular that this applies to yk hk, because we're basically taking the kth output unit and comparing that to the value of yk, which is one of those vectors saying what class it should be. And finally, the second term here is the regularization term, similar to what we had for logistic regression. This summation terms looks really complicated, but all it's doing is just summing over these terms theta, j, I, l for all values of I, j, and l, except that we don't sum over the terms corresponding to these bias values like we had for logistic regression. Concretely, we don't sum over the terms corresponding to where I is equal to 0. So that is because when we're computing the activation of a neuron, we have terms like these, theta I0 plus theta I1 x1 plus and so on, where I guess we could have a 2 there if this is the first hidden layer. And so the values with a 0 there, that corresponds to something that multiplies into an x0 or an a0. And so this is kind of like a bias unit. And by analogy to what we were doing for logistic regression, we won't sum over those terms in our regularization term because we don't want to regularize them and string their values to 0. But this is just one possible convention, and even if you were to sum over, I equals 0 up to SL, it'll work about the same, and it doesn't make a big difference. But maybe this convention of not regularizing the bias term is just slightly more common. So that's the cost function we're going to use to fit our neural network. In the next video, we'll start to talk about an algorithm for trying to optimize the cost function. In the previous video, we talked about a cost function for the neural network. In this video, let's start to talk about an algorithm for trying to minimize the cost function. In particular, we'll talk about the backpropagation algorithm. Here's the cost function that we wrote down in the previous video. What we like to do is try to find parameters theta to try to minimize j of theta. In order to use either gradient descent or one of the advanced optimization algorithms, what we need to do, therefore, is to write code that takes as input the parameters theta and computes j of theta and these partial derivative terms. Remember that the parameters of the neural network are these things, theta superscript L subscript ij, that's a real number, and so these are the partial derivative terms we need to compute. In order to compute the cost function j of theta, we just use this formula up here. And so what I want to do for most of this video is focus on talking about how we can compute these partial derivative terms. Let's start by talking about the case of when we have only one training example. So imagine, if you will, that our entire training set comprises only one training example, which is a pair xy. I'm not going to write x1, y1, just write our one training example as xy. And let's step through the sequence of calculations we would do with this one training example. The first thing we do is we apply forward propagation in order to compute what our hypothesis actually outputs given this input x. Concretely, recall that A1 is the activation values of this first layer, that is the input layer, so we're going to set that to x. And then we're going to compute Z2 equals theta1A1 and A2 equals G, the sigmoid activation function applied to Z2. And this would give us our activations for the first hidden layer, that is for layer 2 of the network. And we also add those bias terms. Next, we apply two more steps of this forward propagation to compute A3 and A4, which is also the output of our hypothesis h of x. So this is our vectorized implementation of forward propagation, and it allows us to compute the activation values for all of the neurons in our neural network. Next, in order to compute the derivatives, we're going to use an algorithm called backpropagation. The intuition of the backpropagation algorithm is that for each node, we're going to compute the term delta superscript L subscript j that's going to somehow represent the error of node j in layer L. So recall that A superscript L subscript j, that's the activation of the jth unit in layer L. And so this delta term is in some sense going to capture our error in the activation of that node, or sort of how we might wish the activation of that node were slightly different. Concretely, taking the example neural network that we have on the right, which has 4 layers, and so capital L is equal to 4. For each output unit, we're going to compute this delta term. So delta for the jth unit in the 4th layer is equal to just the activation of that unit minus what was the actual value observed in our training example. So this term here can also be written h of x subscript j, right? So this delta term is just the difference between what our hypothesis outputs and what was the value of y in our training set, where this y subscript j is the jth element of the vector value y in our labeled training set. And by the way, if you think of delta a and y as vectors, then you can also take this and come up with a vectorized implementation of it, which is just delta 4 gets set as a4 minus y, where here each of these, delta 4, a4, and y, each of these is a vector whose dimension is equal to the number of output units in our network. So we've now computed the error terms delta 4 for our network. What we do next is compute the delta terms for the earlier layers in our network. Here's the formula for computing delta 3. Delta 3 is equal to theta 3 transpose times delta 4, and this dot times, this is the element-wise multiplication operation that we know from MATLAB. So delta 3 transpose delta 4, that's a vector, g prime z3, that's also a vector, and so dot times is an element-wise multiplication between these two vectors. This term g prime of z3, that formally is actually the derivative of the activation function g evaluated at the input values given by z3. If you know calculus, you can try to work it out yourself and see if you can simplify it to the same answer that I get. But I'll just tell you pragmatically what that means. What you do to compute this g prime, these derivative terms, is just a3 dot times 1 minus a3, where a3 is the vector of activations, 1 is the vector of ones, and a3 is again the activation, the vector of activation values for that layer. Next, you apply a similar formula to compute delta 2, where again that can be computed using a similar formula, only now is a2, like so. And I didn't prove it here, but you can actually, it's possible to prove if you know calculus that this expression is equal to mathematically the derivative of the g function, of the activation function, which I'm denoting by g prime. And finally, that's it. And there is no delta 1 term, because the first layer corresponds to the input layer, and that's just the features we observed in our training set. So that doesn't have any error associated with it. It's not like, we don't really want to try to change those values. And so we have delta terms only for layers 2, 3, and 4 in this example. The name backpropagation comes from the fact that we start by computing the delta term for the output layer, and then we go back a layer and compute the delta terms for the third hidden layer, and then we go back another step to compute delta 2. And so we're sort of backpropagating the errors from the output layer to layer 3 to layer 2, hence the name backpropagation. Finally, the derivation is surprisingly complicated and surprisingly involved, but if you just do these few steps of computation, it's possible to prove via, frankly, somewhat complicated mathematical proof. It's possible to prove that if you ignore regularization, then the partial derivative terms you want are exactly given by the activations and these delta terms. This is ignoring lambda, or alternatively, if the regularization term lambda were equal to 0. We'll fix this detail later about the regularization term. But so by performing backpropagation and computing these delta terms, you can, pretty quickly compute these partial derivative terms for all of your parameters. So this is a lot of detail. Let's take everything and put it all together to talk about how to implement backpropagation to compute derivatives with respect to your parameters, and for the case of when we have a large training set, not just a training set of one example. Here's what we do. Suppose we have a training set of m examples like that shown here. The first thing we're going to do is we're going to set these delta L subscript ij. So this triangle symbol, that's actually the capital Greek alphabet delta. The symbol we had on the previous slide was the lowercase delta. So the triangle is capital delta. We're going to set this equal to 0 for all values of Lij. Eventually, this capital delta Lij will be used to compute the partial derivative term, partial derivative with respect to theta Lij of j of theta. So as we'll see in a second, these deltas are going to be used as accumulators that will slowly add things to in order to compute these partial derivatives. Next, we're going to loop through our training set. So we'll say for I equals 1 through m. And so for the ith iteration, we're going to be working with the training example xi, yi. So the first thing we're going to do is set A1, which is the activations of the input layer, set that to be equal to xi, that is the inputs for our ith training example. And then we're going to perform forward propagation to compute the activations for layer 2, layer 3, and so on up to the final layer, layer capital L. Next, we're going to use the output label yi from the specific example that we're looking at to compute the error term delta L for the output layer. So delta L is what a hypothesis output minus what the target label was. And then we're going to use the backpropagation algorithm to compute delta L minus 1, delta L minus 2, and so on down to delta 2. And once again, there is no delta 1 because we don't associate an error term with the input layer. And finally, we're going to use these capital delta terms to accumulate these partial derivative terms that we wrote down on the previous slide. And by the way, if you look at this expression, it's possible to vectorize this too. Concretely, if you think of delta ij as a matrix indexed by subscript ij, then if delta L is a matrix, you can rewrite this as delta L gets updated as delta L plus lowercase delta L plus 1 times A L transpose. So that's a vectorized implementation of this that automatically does this update for all values of I and j. Finally, after executing the body of the for loop, we then go outside the for loop and we compute the following. We compute capital D as follows. And we have two separate cases for j equals 0 and j not equals 0. The case of j equals 0 corresponds to the bias term. So when j equals 0, that's why we're missing this extra regularization term. Finally, while the formal proof is pretty complicated, what you can show is that once you've computed these d terms, that is exactly the partial derivative of the cost function with respect to each of your parameters. And so you can use those in either gradient descent or in one of the advanced optimization algorithms. So that's the backpropagation algorithm and how you compute derivatives of your cost function for a neural network. I know this looks like it was a lot of details and this was a lot of steps strung together, but both in the programming assignments right out and later in this video, we'll give you a summary of this so that you can have all the pieces of the algorithm together so that you know exactly what you need to implement if you want to implement backpropagation to compute the derivatives of your neural network's cost function with respect to its parameters. In the previous video, we talked about the backpropagation algorithm. To a lot of people seeing it for the first time, the first impression is often that, wow, this is a really complicated algorithm and there are all these different steps and I'm not quite sure how they fit together and it's like kind of a black box with all these complicated steps. In case that's how you're feeling about backpropagation, that's actually okay. Backpropagation, maybe unfortunately, is a less mathematically clean or less mathematically simple algorithm compared to linear regression or logistic regression. And I've actually used backpropagation, pretty successfully for many years, and even today I still don't sometimes feel like I have a very good sense of just what it's doing or sort of intuition about what backpropagation is doing. If for those of you that are doing the programming exercises, that will at least mechanically step you through the different steps of how to implement backprop, so you'll be able to get it to work for yourself. And what I want to do in this video is look a little bit more at the mechanical steps of backpropagation and try to give you a little more intuition about what the mechanical steps of backprop is doing to hopefully convince you that it's at least a reasonable algorithm. In case, even after this video, in case backpropagation still seems very black box and kind of like too many complicated steps and a little bit magical to you, that's actually okay. And even though I've used backprop for many years, sometimes it's a difficult algorithm to understand. But hopefully this video will help a little bit. In order to better understand backpropagation, let's take another closer look at what forward propagation is doing. Here's the neural network with two input units, that is not counting the bias unit, and two hidden units in this layer, and two hidden units in the next layer, and then finally one output unit. And again, these counts 2, 2, 2 are not counting these bias units on top. In order to illustrate forward propagation, I'm going to draw this network a little bit differently. And in particular, I'm going to draw this neural network with the nodes drawn as these very fat ellipses so that I can write text in them. When performing forward propagation, we might have some particular example, say some example xi comma yi, and it will be this xi then we feed into the input layer. So this is maybe xi1 and xi2 are the values we set the input layer to. And when we forward propagate it to the first hidden layer here, what we do is compute z21 and z22. So these are the weighted sum of inputs of the input units. And then we apply the sigmoid or the logistic function, and the sigmoid activation function applied to the z value gives us these activation values. So that gives us a21 and a22. And then we forward propagate again to get, here z31, apply the sigmoid or the logistic function, the activation function to that to get a31, and similarly like so, until we get z41, apply the activation function. This gives us a41, which is the final output value of the neural network. Let's erase this arrow to give myself some more space. And if you look at what this computation really is doing, focusing on this hidden unit, let's say, we have that this weight, shown in magenta there, is my weight theta210. The indexing is that important. And this weight here, which I guess I'm highlighting in red, that is theta211. And this weight here, which I'm drawing in green in cyan, is theta212. So the way we compute this value, z31 is as equal to this magenta weight times this value. So that's theta210 times 1. And then plus this red weight times this value. So that's theta211 times a21. And finally, this cyan weight times this value, which is therefore plus theta212 times a21. And so that's forward propagation. And it turns out that, as we'll see later in this video, what backpropagation is doing a process very similar to this, except that instead of the computations flowing from the left to the right of this network, the computations instead flow from the right to the left of the network, and using a very similar computation as this. And I'll say in 2 slides exactly what I mean by that. To better understand what backpropagation is doing, let's look at the cost function. Here's the cost function that we had for when we have only one output unit. If we have more than one output unit, we used to have a summation over the output units indexed by k there. But if you have only one output unit, then this is a cost function. And we do forward propagation and backpropagation on one example at a time. So let's just focus on a single example, xiyi, and focus on the case of having one output unit. So yi here is just a real number. And let's ignore regularization, so lambda equals 0, and this final term, that regularization term, goes away. Now, if you look inside this summation, you find that the cost term associated with the ith training example, that is the cost associated with training example xiyi, that's going to be given by this expression. The cost of training example I is written as follows. And what this cost function does is it plays a role similar to the squared error. So rather than looking at this complicated expression, if you want, you can think of cost of I being approximately, the squared difference between what the neural network outputs versus what was the actual value. Just as in logistic regression, we actually prefer to use the slightly more complicated cost function using the log, but for the purpose of intuition, feel free to think of the cost function as being this sort of squared error cost function. And so this cost of I measures how well is the network doing on correctly predicting example I. How close is the output to the actual observed label yi. Now let's look at what backpropagation is doing. One useful intuition is that backpropagation is computing these delta superscript L subscript J terms, and we can think of these as the quote error of the activation value that we got for unit J in the ELF layer. More formally, and this is maybe only for those of you that are familiar with calculus, more formally, what the delta terms actually are is this. They're the partial derivative with respect to ZLJ, that is this weighted sum of inputs that we're computing, these Z terms, partial derivative with respect to these things of the cost function. So concretely, the cost function is a function of the label Y and of the value, this h of x, output by a neural network. And if we could go inside the neural network and just change those ZLJ values a little bit, then that will affect these values that the neural network is outputting, and so that will end up changing the cost function. And again, really, this is only for those of you that are expert in calculus. If you're comfortable with partial derivatives, what these delta terms are is they turn out to be the partial derivative of the cost function with respect to these intermediate terms that we're computing. And so they're a measure of how much would we like to change the neural network's weights in order to affect these intermediate values of the computation, so as to affect the final output of the neural network h of x and therefore affect the overall cost. In case this last part of this partial derivative intuition, in case that didn't make sense, don't worry about it. The rest of this we can do without really talking about partial derivatives. But let's look in more detail about what backpropagation is doing. For the output layer, it first sets this delta term, let's say delta 4,1, as yi, if we're doing forward propagation and backpropagation on this training example I. It says this yi minus a41. So this is really the error, right? It's the difference between the actual value of y minus what was the value predicted. And so we're going to compute delta 41 like so. Next, we're going to propagate these values backwards. I explained this in a second, and end up computing the delta terms of the previous layer. We're going to end up with delta 3,1, delta 3,2, and then we're going to propagate this further backward and end up computing delta 2,1 and delta 2,2. Now, the backpropagation calculation is a lot like running the forward propagation algorithm, but doing it backwards. So here's what I mean. Let's look at how we end up with this value of delta 2,2. So we have delta 2,2. And similar to forward propagation, let me label a couple of the weights. So this weight, which I'm going to draw in cyan, let's say that weight is theta 2 of 1, 2. And this weight down here, let me highlight this in red, that's going to be, let's say, theta 2 of 2, 2. So if we look at how delta 2, 2 is computed, how it's computed for this node, it turns out that what we're going to do is we're going to take this value and multiply by this weight and add it to this value multiplied by that weight. So it's really a weighted sum of these delta values weighted by the corresponding edge strength. So concretely, let me fill this in. This delta 2, 2 is going to be equal to theta 2, 1, 2, which is that magenta weight, times delta 3, 1, plus, and then the thing I had in red, that's theta 2, 2, 2 times delta 3, 2. So it's really literally this red weight times this value plus this magenta weight times this value, and that's how we wind up with that value of delta. And just as another example, let's look at this value. How do we get that value? Well, it's a similar process. If this weight, which I'm going to highlight in green, if this weight is equal to, say, delta 312, then we have that delta 32 is going to be equal to that green weight, theta 312 times delta 41. And by the way, so far I've been writing the delta values only for the hidden units but excluding the biased units. Depending on how you define the backpropagation algorithm, or depending on how you implement it, you may end up implementing something to compute delta values for these biased units as well. The bias units always output the value of +1, and they are just what they are, and there's no way for us to change the value. And so depending on your implementation of backprop, the way I usually implement it, I do end up computing these delta values, but we just discard them and we don't use them because they don't end up being part of the calculation needed to compute the derivatives. So hopefully that gives you a little better intuition about what backpropagation is doing. In case of all of this still seems somewhat magical and somewhat black box, in a later video, in the putting it together video, I'll try to give a little bit more intuition about what backpropagation is doing. But unfortunately, this is a difficult algorithm to try to visualize and understand what it's really doing. But fortunately, I guess many people have been using it very successfully for many years. And if you implement the algorithm, you can have a very effective learning algorithm, even though the inner workings of exactly how it works can be harder to visualize. In the previous video, we talked about how to use backpropagation to compute the derivatives of your cost function. In this video, I want to quickly tell you about one implementational detail of unrolling your parameters from matrices into vectors, which we'll need in order to use the advanced optimization routines. Concretely, let's say you've implemented a cost function that takes as input your parameters theta and returns the cost function and returns derivatives. Then you can pass this to an advanced optimization algorithm like fmin-unc, and fmin-unc isn't the only one, by the way. There are also other advanced optimization algorithms, but what all of them do is take as input a pointer to the cost function and some initial value of theta. And these routines assume that theta and the initial value of theta, that these are parameter vectors, maybe Rn or Rn plus 1, but that these are vectors. And it also assumes that your cost function will return as a second return value this gradient, which is also like Rn or Rn plus 1, so also a vector. This worked fine when we were using logistic regression, but now that we're using a neural network, our parameters are no longer vectors, but instead there are these matrices, where for a 4-layer neural network we would have parameter matrices theta 1, theta 2, theta 3 that we might represent in octave as these matrices theta 1, theta 2, theta 3. And similarly, these gradient terms that we're expected to return, well, in the previous video we showed how to compute these gradient matrices, which was capital D1, capital D2, capital D3, which we might represent in octave as matrices D1, D2, D3. In this video, I want to quickly tell you about the idea of how to take these matrices and unroll them into vectors so that they end up being in a format suitable for passing into as theta here or for getting out for a gradient there. Concretely, let's say we have a neural network with one input layer with 10 units, a hidden layer with 10 units, and one output layer with just 1 unit. So S1 is the number of units in layer 1, S2 is the number of units in layer 2, and S3 is the number of units in layer 3. In this case, the dimension of your matrices theta and d are going to be given by these expressions. So for example, theta 1 is going to be a 10 by 11 matrix, and so on. So in octave, if you want to convert between these matrices and vectors, what you can do is take your theta 1, theta 2, theta 3 and write this piece of code, and this will take all the elements of your 3 theta matrices. You can take all the elements of theta 1, all the elements of theta 2, all the elements of theta 3, and unroll them and put all the elements into a big long vector, which is theta vec. And similarly, the second command would take all of your D matrices and unroll them into a big long vector and call it dvec. And finally, if you want to go back from the vector representations to the matrix representations, what you do to get back theta 1, say, is take theta vec and pull out the first 110 elements. So theta 1 has 110 elements because it's a 10 by 11 matrix. So that pulls out the first 110 elements, and then you can use the reshape command to reshape this back into theta 1. And similarly, to get back theta 2, you pull out the next 110 elements and reshape it. And for theta 3, you pull out the final 11 elements and run reshape to get back theta 3. Here's a quick octave demo of that process. So for this example, let's set theta 1 equal to be ones of 10 by 11. So it's a matrix of all ones. And just to make this easier to see, let's set that to be 2 times ones 10 by 11. And let's set theta 3 equals 3 times ones of 1 by 11. So this is 3 separate matrices, theta 1, theta 2, theta 3. If I want to put all of these into a vector, I set theta vec equals theta 1 semicolon theta 2 theta 3. Right, there's a colon in the middle, and like so. And now theta vec is going to be a very long vector. There's 231 elements. If I display it, I find that it's this very long vector with all the elements of the first matrix, all the elements of the second matrix, then all the elements of the third matrix. And if I want to get back my original matrices, I can do reshape theta vec. Let's pull out the first 110 elements and reshape that into a 10 by 11 matrix. And this gives me back theta 1. And if I then pull out the next 110 elements, so that's indices 111 to 220, I get back all of my 2's. And if I go from 221 up to the last element, which is element 231, and reshape to 1 by 11, I get back theta 3. To make this process really concrete, here's how we use the unrolling idea to implement our learning algorithm. Let's say that you have some initial value of the parameters theta 1, theta 2, theta 3. What we're going to do is take these and unroll them into a long vector we're going to call initial theta to pass into fmin unc as this initial setting of the parameters theta. The other thing we need to do is implement the cost function. Here's my implementation of the cost function. The cost function is going to give as input theta vec, which is going to be all of my parameter vectors that in the form that's been unrolled into a vector. So the first thing I'm going to do is I'm going to use theta vec, and I'm going to use the reshape function, so pull out elements from theta vec and use reshape to get back my original parameter matrices theta 1, theta 2, theta 3. So these are going to be matrices that I'm going to get. So that gives me a more convenient form in which to use these matrices so that I can run forward propagation and back propagation to compute my derivatives and to compute my cost function j of theta. And finally, I can then take my derivatives and unroll them, so keeping the elements in the same ordering as I did when I unrolled my thetas. But I'm going to unroll d1, d2, d3 to get gradient vec, which is now what my cost function can return. It can return a vector of these derivatives. So hopefully you now have a good sense of how to convert back and forth between the matrix representation of the parameters versus the vector representation of the parameters. The advantage of the matrix representation is that when your parameters are stored as matrices, it's more convenient when you're doing forward propagation and back propagation, and it's easier when your parameters are stored as matrices to take advantage of the sort of vectorized implementations. Whereas in contrast, the advantage of the vector representation, when you have like theta vec or d vec, is that when you're using the advanced optimization algorithms, those algorithms tend to assume that you have all of your parameters unrolled into a big long vector. And so with what we just went through, hopefully you can now quickly convert between the two as needed. In the last few videos, we talked about how to do forward propagation and back propagation in a neural network in order to compute derivatives. But backprop as an algorithm has a lot of details and, can be a little bit tricky to implement. And one unfortunate property is that there are many ways to have subtle bugs in backprop, so that if you run it with gradient descent or some other optimization algorithm, it could actually look like it's working, and your cost function j of theta may end up decreasing on every iteration of gradient descent, but this could hold true even though there might be some bug in your implementation of backprop. So it looks like j of theta is decreasing, but you might just wind up with a neural network that has a higher level of error than you would with a bug-free implementation, and you might just not know that there was this subtle bug that's giving you worse performance. So what can we do about this? There's an idea called gradient checking that eliminates almost all of these problems. So today, every time I implement backpropagation or a similar gradient descent algorithm on a neural network or any other reasonably complex model, I always implement gradient checking. And if you do this, it will help you make sure and sort of gain high confidence that your implementation of forward prop and backprop or whatever is 100% correct. And in what I've seen, this pretty much eliminates all the problems associated with sort of buggy implementations of backprop. And in the previous videos, I sort of asked you to take on faith that the formulas I gave for computing the deltas and the d's and so on, I asked you to take on faith that those actually do compute the gradients of the cost function. But once you implement numerical gradient checking, which is the topic of this video, you'll be able to sort of verify for yourself that the code you're writing is indeed computing the derivative of the cost function j. So here's the idea. Consider the following example. Suppose I have a function j of theta, and I have some value theta, and for this example, I'm going to assume that theta is just a real number. And let's say I want to estimate the derivative of this function at this point. And so the derivative is equal to the slope of that sort of tangent line. Here's how I'm going to numerically approximate the derivative, or rather, here's a procedure for numerically approximating the derivative. I'm going to compute theta plus epsilon, so value a little bit to the right, and I'm going to compute theta minus epsilon, and I'm going to look at those 2 points and connect them by a straight line, and I'm going to connect these 2 points by a straight line, and I'm going to use the slope of that little red line as my approximation to the derivative, which is the true derivative is the slope of that blue line over there. So, it seems like it would be a pretty good approximation. Mathematically, the slope of this red line is this vertical height divided by this horizontal width. So this point on top is j of theta plus epsilon. This point here is j of theta minus epsilon, so this vertical difference is j of theta plus epsilon minus j of theta minus epsilon, and this horizontal distance is just 2 epsilon. So my approximation is going to be that the derivative with respect to theta of j of theta at this value of theta, that's approximately j of theta plus epsilon minus j of theta minus epsilon over 2 epsilon. Usually I'll use a pretty small value for epsilon and set epsilon to be maybe on the order of 10 to the minus 4. There's usually a large range of different values for epsilon that work just fine, and in fact if you let epsilon become really small, then mathematically this term here actually mathematically becomes the derivative, becomes exactly the slope of the function at this point. It's just that we don't want to use epsilon that's too small, because then you might run into numerical problems. So I usually use epsilon around 10 to the minus 4, say. And by the way, some of you may have seen an alternative formula for estimating the derivative, which is this formula. This one on the right is called the one-sided difference, whereas the formula on the left, that's called the two-sided difference. The two-sided difference gives us a slightly more accurate estimate, so I usually use that rather than this one-sided difference estimate. So concretely, what you implement in Octave is you implement the following. You implement code to compute grad approx, which is going to be our approximation to the derivative as just this formula, j of theta plus epsilon minus j of theta minus epsilon divided by 2 times epsilon. And this will give you a numerical estimate of the gradient at that point. And in this example, it seems like it's a pretty good estimate. Now, on the previous slide, we considered the case of when theta was a real number. Now let's look at a more general case of when theta is a vector parameter. So let's say theta is an Rn, and it might be an unreal version of the parameters of our neural network. So theta is a vector that has n elements, theta 1 up to theta n. We can then use a similar idea to approximate all the partial derivative terms. Concretely, the partial derivative of a cost function with respect to the first parameter, theta 1, that can be obtained by taking j and increasing theta 1. So you have j of theta 1 plus epsilon and so on, minus j of this theta 1 minus epsilon and divided by 2 epsilon. The partial derivative with respect to the second parameter, theta 2, is again this thing, except that you take j of, here you're increasing theta 2 by epsilon, and here you're decreasing theta 2 by epsilon, and so on, down to the derivative with respect to theta n would be if you increase and decrease theta n by epsilon over there. So these equations give you a way to numerically approximate the partial derivative of j with respect to any one of your parameters, theta I. Concretely, what you implement is therefore the following. We implement the following in octave to numerically compute the derivatives. We say for I equals 1 through n, where n is the dimension of our parameter vector theta, and I usually do this with the unrolled version of the parameters. So theta is just a long list of all of my parameters in my neural network, say. I'm going to set theta plus equals theta, then increase theta plus the ith element by epsilon, and so this is basically theta plus is equal to theta except for theta plus I, which is now incremented by epsilon. So theta plus is equal to theta 1, theta 2, and so on, and then theta I has epsilon added to it, and then I go down to theta n. So this is what theta plus is. And similarly, these two lines set theta minus to something similar, except that this, instead of theta I plus epsilon, this now becomes theta I minus epsilon. And then finally, you implement this, grad approx I, and this will give you your approximation to the partial derivative with respect to theta I of j of theta. And the way we use this in our neural network implementation is we would implement this for loop to compute the partial derivative of the cost function with respect to every parameter in our network. And we can then take the gradient that we got from backprop. So dvec was the derivatives we got from backprop. So backpropagation was a relatively efficient way to compute the derivatives or the partial derivatives of our cost function with respect to all of our parameters. And what I usually do is then take my numerically computed derivative, that is this grad approx that we just had from up here, and make sure that that is equal, or sort of approximately equal up to small values of numerical roundoff, that is pretty close to the dvec that I got from backprop. And if these two ways of computing the derivative give me the same answer, or at least give me very similar answers, up to a few decimal places, then I'm much more confident that my implementation of backprop is correct. And when I plug these dvec vectors into gradient descent or some advanced optimization algorithm, I can then be much more confident that I'm computing the derivatives correctly, and therefore that hopefully my code will run correctly and do a good job optimizing j of theta. Finally, I want to put everything together and tell you how to implement this numerical gradient checking. Here's what I usually do. First thing I do is implement backpropagation to compute dvec. So this is a procedure we talked about in the earlier video to compute dvec, which may be our unrolled version of these matrices. Then what I do is implement numerical gradient checking to compute grad approx. So this was what I described earlier in this video in the previous slide. Then you should make sure that dvec and grad approx give similar values, let's say up to a few decimal places. And finally, and this is the important step, before you start to use your code for learning, for seriously training your network, it's important to turn off gradient checking and to no longer compute this grad approx thing using the numerical derivative formulas that we talked about earlier in this video. And the reason for that is the numerical gradient checking code, the stuff we talked about in this video, that's a very computationally expensive, that's a very slow way to try to approximate the derivative. Whereas in contrast, the backpropagation algorithm that we talked about earlier, that is the thing we talked about earlier for computing D1, D2, D3, or for dvec, backprop is a much more computationally efficient way of computing the derivatives. So once you've verified that your implementation of backpropagation is correct, you should turn off gradient checking and just stop using that. So just to reiterate, you should be sure to disable your gradient checking code before running your algorithm for many iterations of gradient descent or for many iterations of the advanced optimization algorithms in order to train your classifier. Concretely, if you were to run numerical gradient checking on every single iteration of gradient descent, or if it were in the inner loop of your cost function, then your code would be very slow because the numerical gradient checking code is much slower than the backpropagation algorithm, than the backpropagation method, where you remember we were computing delta 4, delta 3, delta 2, and so on. That was the backpropagation algorithm. That is a much faster way to compute derivatives than gradient checking. So when you're ready, once you verify the implementation of backpropagation is correct, make sure you turn off or you disable your gradient checking code while you're training your algorithm, or else your code could run very slowly. So that's how you take gradients numerically, and that's how you can verify that your implementation of backpropagation is correct. Whenever I implement backpropagation or similar gradient descent algorithm for a complicated model, I always use gradient checking, and this really helps me make sure that my code is correct. In the previous videos, we put together almost all the pieces you need in order to implement and train a neural network. There's just one last idea I need to share with you, which is the idea of random initialization. When you're running an algorithm like gradient descent or also the advanced optimization algorithms, we need to pick some initial value for the parameters theta. So for the advanced optimization algorithm, it assumes that you will pass it some initial value for the parameters theta. Now let's consider gradient descent. For that, we also need to initialize theta to something, and then we can slowly take steps that go downhill using gradient descent to go downhill to minimize the function j of theta. So what can we set the initial value of theta to? Is it possible to set the initial value of theta to the vector of all zeros? Whereas this worked okay when we were using logistic regression, initializing all of your parameters to 0 actually does not work when you're training a neural network. Consider training the following neural network, and let's say we initialize all the parameters in the network to 0. And if you do that, then what that means is that at the initialization, this blue weight, that I'm coloring in blue, is going to equal to that weight, so they're both 0. And this weight that I'm coloring in red is equal to that weight, which I'm coloring in red. And also this weight, which I'm coloring in green, is going to equal to the value of that weight. And what that means is that both of your hidden units, A1 and A2, are going to be computing the same function of your inputs, and thus you end up with, for every one of your training examples, you end up with A21 equals A22. And moreover, because I'm not going to show this in too much detail, but because these outgoing weights are the same, you can also show that the delta values are also going to be the same. So concretely, you end up with delta 11, delta 21 equals delta 22. And if you work through the math further, what you can show is that the partial derivatives with respect to your parameters will satisfy the following: that the partial derivative of the cost function with respect to, I'm writing out the derivatives with respect to these two blue weights in your network, you find that these two partial derivatives are going to be equal to each other. And so what this means is that even after, say, one gradient descent update, you're going to update, say, this first blue weight with learning rate times this, and you're going to update the second blue weight with some learning rate times this. But what this means is that even after one gradient descent update, those two blue weights, those two blue colored parameters will end up the same as each other. So there'll be some non-zero value now, but this value will equal to that value. And similarly, even after one gradient descent update, this value will equal to that value. There'll be some non-zero values, just that the two red values will equal to each other. And similarly, the two green weights, they'll both change values, but they'll both end up the same value as each other. So after each update, the parameters corresponding to the inputs going to each of the two hidden units are identical. That's just saying that the two green weights are still the same, the two red weights are still the same, the two blue weights are still the same. And what that means is that even after one iteration of, say, gradient descent, you find that your two hidden units are still computing exactly the same function of the input. So you still have this A12 equals A22. And so you're back to this case. And as you keep running gradient descent, the blue weights, the two blue weights will stay the same as each other, the two red weights will stay the same as each other, the two green weights will stay the same as each other. And what this means is that your neural network really can't compute very interesting functions, right? Imagine that you had not only two hidden units, but imagine that you had many, many hidden units. Then what this is saying is that all of your hidden units are computing the exact same feature. All of your hidden units are computing the exact same function of the input. And this is a highly redundant representation, because that means that your final logistic regression unit really gets to see only one feature, because all of these are the same. And this prevents your neural network from learning something interesting. In order to get around this problem, the way we initialize the parameters of a neural network, therefore, is with random initialization. Concretely, the problem we saw on the previous slide is sometimes called the problem of symmetric weights, that is, of the weights all being the same. And so this random initialization is how we perform symmetry breaking. So what we do is we initialize each value of theta to a random number between minus epsilon and epsilon. So this is a notation to mean numbers between minus epsilon and plus epsilon. So my weights or my parameters are all going to be randomly initialized between minus epsilon and plus epsilon. The way I write code to do this in Octave is I might set theta 1 to be equal to this. So this rand 10 by 11, that's how you compute a random 10 by 11 dimensional matrix, and all the values are between 0 and 1. So these are going to be real numbers that take on any continuous values between 0 and 1. And so if you take a number between 0 and 1, multiply it by 2 times in an epsilon, then minus in an epsilon, then you end up with a number that's between minus epsilon and plus epsilon. And incidentally, this epsilon here has nothing to do with the epsilon that we were using when we were doing gradient checking. So when we're doing numerical gradient checking, there we were adding some values of epsilon to theta. This is a unrelated value of epsilon, which is why I'm denoting init epsilon, just to distinguish it from the value of epsilon we were using in gradient checking. And similarly, if you want to initialize theta 2 to a random 1 by 11 matrix, you can do so using this piece of code here. So, to summarize, to train a neural network, what you should do is randomly initialize the weights to small values close to 0, between minus epsilon and plus epsilon, say, and then implement backpropagation, do gradient checking, and use either gradient descent or one of the advanced optimization algorithms to try to minimize j of theta as a function of the parameters theta, starting from this randomly chosen initial value for the parameters. And by doing symmetry breaking, which is this process, hopefully gradient descent or the advanced optimization algorithms will be able to find a good value of theta. So it's taken us a lot of videos to get through the neural network learning algorithm. In this video, what I'd like to do is try to put all the pieces together to give an overall summary or a bigger picture view of how all the pieces fit together and of the overall process for how to implement a neural network learning algorithm. When training a neural network, the first thing you need to do is pick some network architecture. And by architecture, I just mean connectivity pattern between the neurons. So, we might choose between, say, a neural network with 3 input units and 5 hidden units and 4 output units versus one with 3, 5 hidden, 4 output, and here 3, 5 units in each of 3 hidden layers and 4 output units. And so these choices of how many hidden units in each layer and how many hidden layers, those are architecture choices. So how do you make these choices? Well, first, the number of input units, well, that's pretty well defined. And once you've decided on a fixed set of features x, the number of input units will just be the dimension of your features xi will be determined by that. And if you're doing multi-class classification, the number of output units will be determined by the number of classes in your classification problem. And just a reminder, if you have a multi-class classification where y takes on, say, values between 1 and 10, so that you have 10 possible classes, then remember to rewrite your outputs y as these sorts of vectors, right? So instead of class 1, you recode it as a vector like that. Or for the second class, you recode it as a vector like that. So if one of your examples is takes on the fifth class, y equals 5, then what you're showing to your neural network is not actually a value of y equals 5. Instead, here at the output layer, which would have 10 output units, you would instead feed it a vector, which with a 1 in the 5th position, and then a bunch of zeros down here. Right? So the choice of number of input units and number of output units is maybe somewhat reasonably straightforward. And as for the number of hidden units and the number of hidden layers, a reasonable default is to use a single hidden layer. So this type of neural network shown on the left with just one hidden layer is probably the most common. Or if you use more than one hidden layer, again, a reasonable default will be to have the same number of hidden units in every single layer. So here we have 2 hidden layers, and each of these hidden layers has the same number, 5 of hidden units, and here we have 3 hidden layers, and each of them has the same number, that is 5 hidden units. But rather than doing this sort of network architecture on the left would be a perfectly reasonable default. And as for the number of hidden units, usually the more hidden units the better. It's just that if you have a lot of hidden units, it can become more computationally expensive, but very often having more hidden units is a good thing. And usually the number of hidden units in each layer will be maybe comparable to the dimension of x, comparable to the number of features, or it could be anywhere from same number of hidden units as input features to maybe twice of that to 3 or 4 times of that. So having a number of hidden units is comparable, or several times or somewhat bigger than the number of input features is often a useful thing to do. So hopefully this gives you one reasonable set of default choices for network architecture. And if you follow these guidelines, you probably get something that works well. But in a later set of videos where I'll talk specifically about advice for how to apply learning algorithms, I'll actually say a lot more about how to choose a neural network architecture. I actually have quite a lot more to say later about how to make good choices for the number of hidden units, number of hidden layers, and so on. Next, here's what we need to implement in order to train a neural network. There are actually 6 steps that I have. I have 4 on this slide and 2 more steps on the next slide. First step is to set up the neural network and to randomly initialize the values of the weights. And we usually initialize the weights to small values near 0. Then we implement forward propagation so that we can input any input x to the neural network and compute h of x, which is this output vector of the y values. We then also implement code to compute this cost function j of theta. And next we implement backprop or the backpropagation algorithm to compute these partial derivatives terms, partial derivatives of j of theta with respect to the parameters. Concretely, to implement backprop, usually we will do that with a for loop over the training examples. Some of you may have heard of advanced, frankly, very advanced vectorization methods where you don't have a for loop over the M training examples, but the first time you're implementing backprop, there should almost certainly be a for loop in your code where you're iterating over the examples, x1, y1, then so you do forward prop and backprop on the first example, and then in the second iteration of the for loop, you do forward propagation and backpropagation on the second example, and so on until you get through the final example. So there should be a for loop in your implementation of backprop, at least the first time you're implementing it. And then there are, frankly, somewhat complicated ways to do this without a for loop, but I definitely do not recommend trying to do that much more complicated version the first time you're trying to implement backprop. So concretely, we have a for loop over my M training examples, and inside the for loop, we're going to perform forward prop and back prop using just this one example. And what that means is that we're going to take xi and feed that to my input layer, perform forward prop, perform back prop, and that will give me all of these activations and all of these delta terms for all of the layers of all of my units in the neural network. Then, still inside this for loop, let me draw some curly braces just to show the scope of the for loop. This isn't Octave code, of course, but it's more like C++ Java code. But the for loop encompasses all this. We're going to compute those delta terms, which here's the formula that we gave earlier. plus delta L plus 1 times A L transpose, and then the sum of the code. And then finally, outside the for loop, having computed these delta terms, these accumulation terms, we would then have some other code, and then that will allow us to compute these partial derivative terms, right? And these partial derivative terms have to take into account the regularization term lambda as well. And so those formulas were given in an earlier video. So having done that, you now hopefully have code to compute these partial derivative terms. Next, in step 5, what I do is then use gradient checking to compare these partial derivative terms that were computed. So compare the versions computed using backpropagation versus the partial derivatives computed using the numerical estimates, that is using numerical estimates of the derivatives. So do gradient checking to make sure that both of these give you very similar values. Having done gradient checking, this now reassures us that our implementation of backpropagation is correct, and is then very important that we disable gradient checking, because the gradient checking code is computationally very slow. And finally, we then use an optimization algorithm such as gradient descent, or one of the advanced optimization methods such as LBFGS, conjugate gradient, as embodied in sort of FMIN, UNC, or other optimization methods. We use these together with backpropagation. So backpropagation is the thing that computes these partial derivatives for us. And so we know how to compute the cost function, we know how to compute the partial derivatives using backpropagation. So we can use one of these optimization methods to try to minimize J of theta as a function of the parameters theta. And by the way, for neural networks, this cost function J of theta is non-convex, or is not convex, and so it can theoretically be susceptible to local minima. And in fact, algorithms like gradient descent and the advanced optimization methods can, in theory, get stuck in local optima. But it turns out that in practice, this is not usually a huge problem. And even though we can't guarantee that these algorithms will find the global optimum, usually algorithms like gradient descent will do a very good job minimizing this cost function J of theta and get to a very good local minimum, even if it doesn't get to the global optimum. Finally, gradient descents for a neural network might still seem a little bit magical. So let me just show one more figure to try to get better intuition about what gradient descent for a neural network is doing. This was actually similar to the figure that I was using earlier to explain gradient descent. So we have some cost function, and we have a number of parameters in our neural network. Right here, I've just written out 2 of the parameter values. In reality, of course, in a neural network, we can have lots of parameters. So these theta 1, theta 2, all of these are matrices, right? So we can have very high dimensional parameters, but because of the limitations of the sorts of plots we can draw, I'm pretending that we have only 2 parameters in this neural network, although obviously we have a lot more in practice. Now, this cost function J of theta measures how well the neural network fits the training data. So if you take a point like this one, down here, that's a point where J of theta is pretty low. And so this corresponds to a setting of the parameters. There's a setting of the parameters theta where, for most of the training examples, the output of my hypothesis, that's maybe pretty close to yi, and if this is true, then that's what causes my cost function to be pretty low. Whereas in contrast, if you were to take a value like that, a point like that corresponds to where for many training examples, the output of my neural network is far from the actual value yi that was observed in the training set. So points like this on the right correspond to where the hypothesis, where the neural network is outputting values on the training set that are far from yi, so it's not fitting the training set well, whereas points like this with low values of the cost function corresponds to where J of theta is low, and therefore corresponds to where the neural network happens to be fitting my training set well, because this is what's needed to be true in order for J of theta to be small. So what gradient descent does is it will start from some random initial point like that out over there, and it will repeatedly go downhill. And so what backpropagation is doing is it's computing the direction of the gradient, and what gradient descent is doing is it's taking little steps downhill until hopefully it gets to, in this case, a pretty good local optimum. So when you implement backpropagation and use gradient descent or one of the advanced optimization methods, this picture sort of explains what the algorithm is doing. It's trying to find a value of the parameters where the output values of the neural network closely matches the values of the yi's observed in your training set. So hopefully this gives you a better sense of how the many different pieces of neural network learning fit together. In case, even after this video, in case you still feel like there are like a lot of different pieces and it's not entirely clear what some of them do or how all of these pieces come together, that's actually okay. Neural network learning and backpropagation is a complicated algorithm, and even though I've seen the math behind backpropagation for many years and I've used backpropagation, I think very successfully for many years, even today I still feel like I don't always have a great grasp of exactly what backpropagation is doing sometimes and of what the optimization process looks like of minimizing J of theta. And this is a much harder algorithm to, I feel like I have a much less good handle on exactly what this is doing compared to, say, linear regression or logistic regression, which were mathematically and conceptually much simpler and much cleaner algorithms. But so in case you feel the same way, that's actually perfectly okay. But if you do implement backpropagation, hopefully what you find is that this is one of the most powerful learning algorithms, and if you implement this algorithm, implement backpropagation, and implement one of these optimization methods, you find that backpropagation will be able to fit very complex, powerful, nonlinear functions to your data, and this is one of the most effective learning algorithms we have today. In this video, I'd like to show you a fun and historically important example of neural network learning, of using a neural network for autonomous driving, that is, getting a car to learn to drive itself. The video that I'll show in a minute was something that I gotten from Dean Pomerleau, who's a colleague who works out in Carnegie Mellon University out on the East Coast of the United States. And in part of the video, you see visualizations like this, and I want to tell you what the visualization looks like before starting the video. Down here on the lower left is the view seen by the car of what's in front of it. And so here, you kind of see a road that's maybe going a bit to the left and then going a little bit to the right. And up here on top, this first horizontal bar shows the direction selected by the human driver and is the location of this bright white band that shows the steering direction selected by the human driver, where here far to the left corresponds to steering hard left, here corresponds to steering hard to the right, and so this location, which is a little bit to the left, a little bit left of center, means that the human driver at this point was steering slightly to the left. And this second bar here corresponds to the steering direction selected by the learning algorithm. And again, the location of this sort of white band means the neural network was here selecting a steering direction that's slightly to the left. And in fact, before the neural network starts learning, initially, you see that the network outputs a gray band, like a gray, uniform gray band throughout this region. And so the uniform gray fuzz corresponds to the neural network having been randomly initialized and initially having no idea how to drive the car, or initially having no idea what direction to steer in. And it's only after it's learned for a while that it will then start to output like a solid white band in just a small part of the region corresponding to choosing a particular steering direction. And that corresponds to when the neural network becomes more confident in selecting a band in one particular location rather than outputting a sort of light gray fuzz, but instead outputting a white band that's more confidently selecting one steering direction.
Alvin is a system of artificial neural networks that learns to steer by watching a person drive. Alvin is designed to control the NavLab 2, a modified Army Humvee equipped with sensors, computers, and actuators for autonomous navigation experiments. The initial step in configuring Alvin is training a network to steer. During training, a person drives the vehicle while Alvin watches. Once every 2 seconds, Alvin digitizes a video image of the road ahead and records the person's steering direction. This training image is reduced in resolution to 30 by 32 pixels and provided as input to Alvin's 3-layered network. Using the backpropagation learning algorithm, Alvin is trained to output the same steering direction as the human driver for that image. Initially, the network steering response is random. After about 2 minutes of training, the network learns to accurately imitate the steering reactions of the human driver. This same training procedure is repeated for other road types. After the networks have been trained, the operator pushes the run switch and Alvin begins driving. 12 times per second, Alvin digitizes an image and feeds it to its neural networks. Each network, running in parallel, produces a steering direction and a measure of its confidence in its response. The steering direction from the most confident network, in this case the network trained for the one-lane road, is used to control the vehicle. Suddenly, an intersection appears ahead of the vehicle. As the vehicle approaches the intersection, the confidence of the one-lane network decreases. As it crosses the intersection and the two-lane road ahead comes into view, the confidence of the two-lane network rises. When its confidence rises, the two-lane network is selected to steer, safely guiding the vehicle into its lane on the two-lane road.
So that was autonomous driving using a neural network. Of course, there are more recently more modern attempts to do autonomous driving. There are a few projects in the US and Europe and so on that are giving more robust driving controllers than this. But I think it's still pretty remarkable and pretty amazing how a simple neural network trained with backpropagation can, actually learn to drive a car somewhat well.